Question 4, we have a particle at a fixed point P, initial velocity u. A we're given as dv dt, v s dt, s is displacement, and we're asked to find an expression for v in terms of uas. But we know that v squared is equal to u squared plus 2as, so that's what we're going to try and get to. So what do we know? We'll just write out what we know. We know s is equal to ut plus a half at squared. So that's where ds dt is equal to u plus at, which is also v, so just keep that in mind. And then if we differentiate v, we'll get a, so differentiating v with respect to t, dv dt is equal to a, and we were given that part, and we were given v is equal to ds dt as well, so we need to come up with something new. So what have we got? Well, v dv ds is also equal to a. I think that's where we start here. Let's see why. Because v is ds dt, and if we multiply that in our chain rule by dv ds, we get dv dt. So I think that's the starting point here. So we take this guy and set up an integral v dv, and that's where the v squared over 2 will come from, or the v squared. That's going to be equal to a with respect to x. So we integrate v and we integrate a with respect to x, a being a constant here, we'll get as on this side. And what do we know at the start? We know that the velocity is equal to u, the initial velocity, when s is equal to the distance displacement is 0. I think that's important here. We put our bands in, that's how we're going to get v and u in here. So integrating v, we're going to get v squared over 2 between v and u will be equal to as between s and 0. So we'll get v squared over 2 minus u squared over 2 is equal to as, and multiplying by 2 we get v squared minus u squared is equal to 2as, and bringing u squared across we'll get v squared is equal to u squared plus 2as. I think that's the approach they want you to take here. Quite a lot of information in part B. We're told that a scientist wants to find the smallest initial velocity u for a rocket on the Earth's surface to escape from the Earth's gravitational field, and this is known as escape velocity. The displacement of the rocket is given by x, time is t. We're given this a here, acceleration, and we're also told that a is dv dx, and we're asked to use this differential equation to find an expression for the velocity of the rocket in terms of all of these things here. So let's see how this starts. We're going to have to say that v dv dx is equal to minus gm. Are we told they're constants? G is a constant, m and r are mass and radius of Earth. So minus gm over r plus x squared. So v dv, we can definitely integrate that, is equal to, now we have the x on the far side, minus gm, seems to be a lot going on here, r plus x squared dx. And what are we told? We're told this here, gm over r squared is equal to g. Kind of hard to see. Gm over r squared is equal to g. So if I say the integral of v dv is equal to the integral, I'll take the minus a, which gm is becoming a, gm over r squared, but I'm going to have to get an r squared into the bottom. Let me see how I can do that. R plus x squared. Now what's that? If I can take that r out, sorry, it's the x squared. The x squared is outside the bracket. Squared is outside. That will help me get the r to be squared. So if I say that's r times, well, that would be 1 to get r, and r times x over r. That's going to give me r plus, well, that's going to give me or plus x. Yeah, it's definitely going to give me or plus x. So that whole expression to be squared is the same as this guy. Or plus or over or, we cancel, get or plus x. So that's equal to or squared times 1 plus x over or to be squared with the product rule. So that's how I can get my or squared into this question. So this whole expression in here, instead of having gm, I'm going to have gm over or squared. I'm going to have just my minus g. And then the or squared, this guy here, will be part of the a that we've brought in here. So I'm going to just integrate, and I'll be left with 1 over. So I'm taking out the gm, and I'll be left with 1 over 1 plus x over or to be squared. So a little bit tricky. I think we're going to have to do integration by parts here. We let u equal, if we let u equal 1 plus x over or, will this help us? 1 plus x over or du dx will be equal to, the 1 disappeared, so what's in front of x? It's just 1x over or, so 1 over or is du dx. That gives me du to be 1 over or dx. And I should have, I have my dx in here, I just didn't write it here. So I have my 1 dx. So what have I got now? I have the integral of this guy, which is the integral of minus a on the outside. We let u equal 1 plus x over r, so it's 1 over u squared dx, or du. Du is equal to my 1 over r dx. So to keep my dx, I actually have to have my or du would be equal to dx. So I'm missing an or in here, and actually what I'll do is I'll factor it out and I'll put it here. So I have minus a or over 1, the integral of 1 over u squared, and u squared is u to the power of minus 2. And if we integrate u to the power of minus 2, we'll get u to the power of minus 1 over minus 1, which is minus 1 over u. So we end up with my, I'll just come up here, v dv, the integral of v dv on the left, which is v squared over 2. And we have bands here. We know that v is equal to u when the displacement, we're doing, it's calling it x this time, x is equal to 0. So that'll help me find c. So if I bring down my answer here, minus, and I see I'm calling ga here, but this is minus g or, and we've integrated it to get minus 1 over u, so that's going to be plus, and then just g or over u, isn't it? And we let u equal 1 plus x over r, so g or over 1 plus x over r. Looks like the integrated part. This seems a bit crazy. So between x, if we put x in, we'll get this value, and if we put 0 in for x, we'll just get g or over 1, or just g or. So the right hand side, I probably shouldn't do it a bit neater, but if we integrate the left, we're going to get v squared over 2 minus u squared over 2, and then the right is going to give me, what do we get? We got g r over 1 plus x over r, and then we got plus, no, it's going to be minus g r, isn't it? The two parts of the integration will be minus the second one, so it's going to be minus g r. This looks ridiculous. What are we asked to get? We're asked for v in terms of all those other guys, so if we multiply by 2, we get v squared minus u squared is equal to 2 g r over 1 plus x over r minus 2 g r, and then v squared will be equal to 2 g r over 1 plus x over r minus 2 g r, and then plus u squared. And if this question doesn't make you love applied maths, then nothing will. So to tidy it up fully, we get v is equal to the square root of this whole expression. And you don't need me to write it out again, but we will substitute into it for the next part. We're told that if r is 6350 kilometers, so that's 6350000 meters, and there was an addendum here: when x tends to infinity, v tends to 0. Calculate the initial velocity. So we're looking for u, so that's why this expression will come in now. So if x tends to infinity, or massive millions and billions on the bottom, will make this tend to 0. So we're just going to get u squared minus 2gr. And we have u. Do we have u? What did they tell us about u? No, we're looking for u. We're looking for u. And we're told that as x tends to 0, so does v actually. So 0 is equal to this expression, the square root of u squared minus 2 by 9.8 by r, which is that 6350000. So u squared will be equal to that expression. If I bring it to the left, if I factor out, multiply or square both sides and bring it to the left, and the square root of this will give me u, and the square root of this on a calculator, it's a massive number, 12446 with 4 zeros is u squared, so then 11156 meters per second, one missing. So that's the end of question 4.